This is example 4.3-5 from the text Conceptual Dynamics. The problem statement reads, if link CD has an angular velocity of 4 radians per second, determine the velocity of point P on link BC and the angular velocity of link AB at the instant shown. So after reading the problem statement, we look at the figure and attempt to understand what's going on. What we have here is sometimes referred to as a 4-bar mechanism. You can see the 3 explicit bars that are linked together, and then the distance between AD can also be sort of thought of as a linkage, the ground. And so what we're given is we're told the rotation of this linkage So we're told that omega CD is 4 radians per second, and we're shown its direction. If we use the right-hand rule and roll the fingers of our right hand in the direction of rotation, our thumb will point out of the page, indicating positive k, or that's how we'll define it. So we'll define x to the right, positive, y up, positive, and so that makes z out of the page positive. So we have 4 positive k radians per second. And as this rotates, it pushes these other linkages. And we want to know the angular velocity of AB and the velocity of point P, where this is point P. So we want to find the velocity of point P and the angular velocity of link AB, where this is link AB. So now that we sort of understand the problem, we know what's given and what we're attempting to find, we can commence with the solution. What we're going to do in solving this problem is follow the procedure given in the book, a general procedure for analyzing mechanisms in general. And in the process, we'll use what we've learned about analyzing the kinematics of rigid bodies. Recalling that rigid bodies have size, we must consider their rotation as well as their translation. And so in the solution, we'll walk through the procedure really quickly to get a sense of sort of our approach, and then we'll sort of repeat the procedure with calculations. So the first step in analyzing a mechanism is to get familiar with the system. And specifically, we want to know, are there any fixed points of rotation or points of known velocity? So we're not told explicitly what the velocity of any of these points are, but we can see that points A and D are fixed. They're pinned to the ground. And so we can deduce that their velocities are 0 because they're not moving. And so knowledge about the velocity of these 2 points will be helpful to us. Another step in the process of getting familiar with the system is to try to identify if there are any constraints. Is any point forced to move in a particular direction? You know, is a pin forced in a slot? Is a body rolling across the ground, sliding across the ground, anything like that? In this case, no. The next thing we want to do is assign angular velocity directions. So we're given what the angular velocity direction is for this bar CD, and we want to attempt to determine what the directions are for the other linkages, AB and BC. If we have trouble determining the directions, that's okay. We'll just go ahead and assume a direction. When we actually do our calculations, if we calculate that the angular velocity is negative, then we know that the direction is opposite what we assumed. So looking at this bar CD, we know it rotates counterclockwise. So as it rotates to the left, it's going to push this bar, and then it's going to push bar AB also to the left. And so it seems natural to assume that as this pushes, bar AB will rotate in that direction, counterclockwise as well. Looking at bar BC, we can see that C is moving in a circle about D, and so it's going to move downward from the point that it's at this instant. Point B is also moving in a circle about A. If we assume this direction of rotation, point B is going to follow a path like that, and so it's going to move up. Since B moves up and C moves down, we can basically deduce that bar BC is going to rotate in the clockwise direction. The second step, after we've gotten familiar with the mechanism, is to analyze the velocities. And our basic approach is to start at a fixed point of rotation and work out, or more generally, to start at a point whose velocity we know and work out from there. In this case, the points whose velocity we know are point A and point D. We can start from either one. In this case, since we're told in essence what the angular velocity of CD is, let's go ahead and start from point D. So we ultimately want to find the velocity of point P. And so the approach is we start at the known point D. From there we can find the velocity of C because C is moving in a circle about D and we know the angular velocity. And then once we know the velocity of point C, we can move from there to the velocity of point P by considering how P moves relative to C. So in math, we'll start from point D, whose velocity we know to be 0, and we'll calculate the velocity of C from D using this relative motion equation. So the velocity of C is equal to the velocity of D plus the velocity of C relative to D. Since C moves relative to D in a circle, we can use our circular motion sort of equations, where omega CD cross the radius of C relative to D. And we know that V sub D is 0 because it's fixed. Once we know the velocity of point C, we can then use that to determine the velocity of point P. So from the first equation, we know what the velocity of C is, and by adding the velocity of P relative to C, we can determine the velocity of P. And again, we can consider P as moving in a circle about point C. And so this is the velocity of P relative to C. This is true of any rigid body motion. We could take any point on the body and consider it as moving in a circle about any other point on the rigid body. And so here we have an equation for calculating the velocity of P, which is ultimately one of the things that we're tasked with finding. The issue that we run into is that we don't know what the angular velocity of this bar is. So we're trying to calculate the velocity of P. We have this equation and we have an unknown that we don't know. So in essence, we're trying to determine the x and y components of VP and implicitly the angular velocity BC. And so we don't have enough equations to solve for those three unknowns. So the solution is to find another equation for the velocity of point P. And basically we're going to start from another point whose velocity we know, point A, and meet in the middle. So we already have a relationship starting at point D, and we're going to get a second relationship starting at point A, and then between those two we'll have enough relationships to solve for the unknowns. So starting from A, we can get a velocity for P that looks like this, where this is the velocity of point B because B is moving in a circle about A. And then this is the velocity of P relative to B, where we're again considering point B as moving in a circle about point B. So if we take this and use the relationship from the previous slide and set them equal to one another, we have two relations for VP. This is the relation starting from point A. This is the relation for VP starting from VD. We set them equal to each other, we have two equations and two unknowns. So we know VC, we know all the radii. The only thing we don't know are the two angular velocities. So looking at this, it appears that we have two unknowns and only one equation. But in reality, we actually have two equations because we have an equation for the x direction and we have an equation for the y direction because these are vectors. Now that we've gone over an approach for solving this problem, we'll actually perform the calculations now. So here we have our figure with our assumed directions for the angular velocities. We've repeated the given information and what it is we're attempting to find. And recall that the approach we're going to take is we're going to find expressions for the velocity of point P starting from one point we know the velocity of, point D, and then a second expression starting from another point whose velocity we know, point A. And between those two expressions, we'll have enough information to solve for all of the unknowns. So beginning from point D, we can find an expression for the velocity of point P. We start from point D, and from there we can find the velocity of C relative to D. And from C, we can find the velocity of P relative to C. Okay. So that gives us our basic relative motion equation. We know the velocity of point D is 0 because point D is fixed. C is moving in a circle about D, so we can use circular motion equations. Omega cross R, where the omega is omega CD, and the position is the position of C relative to D. So this is the velocity of C relative to D. This is actually the velocity of P relative to C. And so in this case, we can think of P as moving in a circle about C. So again, we can use the circular motion equation. In this case, this bar has an angular velocity omega BC, and the position is the position of P relative to C. So that gives us our equation. We can plug in some values. We are given what omega CD is. It is 4 radians per second in the k direction. We cross that with the position of C relative to D. So we think of D as our origin. We draw the position vector towards C. So we can see that it is half a meter. And based on the coordinate frame we're assuming, it's in the positive J direction. And then we have the second cross product. We don't know what omega BC is. It's a variable, but we have assumed a direction for it. If we roll our fingers in this direction, the thumb on our right hand points into the board. So that corresponds to the negative k direction. And the position of P relative to C. C is considered the origin. We draw the position vector towards P. We can see that it's 0.3 meters and it's in the negative I direction. And we can actually perform the cross products. So we have 4 radians per second times 0.5 meters. So that's 2 meters per second. In order to do the k cross the j, I often draw this little figure. And so k cross j is in the direction opposite the drawn arrow. So that corresponds to a negative I. And then for the other cross product, I have negative omega BC cross negative 0.3. So a negative and a negative becomes positive. K cross I results in a positive J. And so this is our first expression for the velocity of point P. Now we're going to do the same process starting at point A. Again, find the velocity of point P. We'll start at A. We can find the velocity of point P relative to A. And then we can find the velocity of P relative to B. Since A is fixed, its velocity is 0. B is moving in a circle about A. So it's equal to the angular velocity of that bar, omega AB, crossed with the position of B relative to A. Then we add, so this is the expression of the velocity of B relative to A. We do the same thing for P relative to B, where again we consider P moving in a circle about B. We again use our angular velocity, omega BC, crossed with the position vector. We have that, we can plug in. So we don't know what omega AB is, but we've assumed a direction. We roll our fingers on our right hand in that direction. Our thumb points out of the paper. So we've assumed it's in the positive k direction. We cross it with the position vector. Consider A the origin. Draw the vector towards the point B. So this vector we can break up into x and y components. The y component is the same as over here. It's 0.5 in the positive j. The x component, we don't know explicitly, but we can find it from geometry where we have a right triangle and this angle of 40 degrees. So we know the side opposite the 40-degree angle, and we want to find the side adjacent to the 40-degree angle. So looking at that, you can use tangent. Tangent of 40 degrees is equal to opposite over adjacent. We multiply the x, divide through by the tangent, and we get that x is approximately 0.596 meters. And so this position vector, we've got a component 0.596 meters in the positive I, plus a component 0.5 in the positive j. So 0.596 positive I plus 0.5 meters in the positive j. And then for the other cross product, again, we don't know what omega BC is. It's a variable, but we've assumed that it's in the negative k direction. And the position of P relative to B, we draw that position vector from the origin towards P. It's in the positive I direction with a magnitude of 0.3 meters. We then can perform these cross products. We have omega AB times 0.596. We have K cross I, which results in a positive J. We have omega AB times 0.5. K cross J is in the negative I. Then we do our second cross product. We have negative omega BC times 0.3. We have K cross I, it's in the positive J. So this gives us our second relationship for VP. We then set them equal to one another. So on the one side, we have negative 2 meters per second in the I, plus 0.3 omega BC in the J. And then equation 2 on the right-hand side. We have only one term in the I direction, negative 0.5 meters. We have two terms in the j direction which we can combine. 0.596 omega AB minus 0.3 omega BC. So looking at this equation, we have two unknowns, omega BC and omega AB. And it may look like we have only one equation, but in fact we have two, because in order for this equality to hold, the I direction components must be equal and the j direction components must be equal. So if we look at the x direction all by itself, on the left-hand side we have negative 2 meters per second, and on the right-hand side we have negative 0.5 meters omega AB. So if we divide through by the negative 0.5, we can solve for omega AB. So negative 2 divided by negative 0.5 is positive 4. The meters cancel. We're left with units of second in the denominator, and it's implicit that there's a radians in the numerator. And so that's what our omega AB is, and that's one of the things we're attempting to find. We're also trying to find the velocity of the point P altogether, and so we also need omega BC. We'll be able to find that by using the y direction equations. And so on the left-hand side, we have 0.3 meters times omega BC. On the right-hand side, we have these terms, 0.596 omega AB, which we just found to be 4, minus 0.3 omega BC. So from this equation, we have only one unknown, the omega BC, and we can solve for that. So over here, we have 0.596 meters, that's 4 radians per second. We add the 0.3 omega BC to this other 0.3 omega BC, we get 0.6 omega BC. We divide through by the 0.6. The meters cancel, and we get approximately 3.97 radians per second. And once we know that, we can then plug that back into either of our expressions for VP. So I'll go ahead and use equation 1 since it's easier. We have that the velocity of P is negative 2 in the I direction. We have 0.3 times omega BC. So 0.3 times 3.97. We multiply that out, still have negative 2 in the I. 0.3 times 3.97 is approximately 11.91, all in the J, and the units work out to be meters per second. And so that is the other quantity we were asked to find.